and this is part 3, the final part of the year-end review lecture. So we're going to start with energy, and energy, we started with fossil fuels, which of course come in 3 different forms. We have the solid form, coal, the liquid, which is our oil, and then the gaseous form, natural gas. And we talked a lot about the advantages, disadvantages, and so forth. You also need to know about their formation. You need to know how long it's going to last, which is the only thing given on this slide. So if you don't remember that information, go back to your charts, go back to your notes, and look at those items. So coal, again, is our most abundant here in the United States. We have enough to last us hundreds of years. The problem is that coal is definitely the dirtiest of our fossil fuels. Even when you clean it, and you hear the term clean coal, it just means that the coal has been scrubbed and removed of impurities before being burned. Those impurities are still going to be located somewhere, and typically that ends up in the water supply. The next one listed is natural gas. We also have natural gas in the United States to last us for a while, and especially since we've discovered the ability to do hydrologic fracturing, we know that we have enough natural gas to last even more than that 50-year supply. Natural gas is a great fossil fuel for heating, so good for your cooking stove, it's good for your household heaters. It is a very clean burning gas. The problem is only when you do hydrologic fracturing that you are releasing some of those contaminants that are pumped into the well, and those are seeping into the groundwater supply. Now, oil, that is by far the one that we are most concerned about running out of. It says here about a decade until supplies peak. I'm pretty sure that supplies are at peak, or globally this is at peak or past peak, based on what we've seen with prices. Now, prices, though, fluctuate based on the political instabilities. They fluctuate based on who's mad at us. They fluctuate based on hurricanes that might come through and disrupt our refineries or the shipping routes. And so when we talk about oil, yes, we still have enough to last us for probably your entire lifetime. The problem is it's going to continue to get more expensive, and it's going to continue to get us into more issues internationally, because the only source that we have domestically is really the Arctic National Wildlife Refuge up in Alaska, and that is protected land because it is a wildlife refuge. The other place where we're getting a lot of our oil right now is from those oil sands that are up in Canada, and we looked at that in the lab and we saw how difficult it was to extract and just how time consuming and intensive as far as other resources that would be. So some important energy facts looking at the history. We used to use firewood, then we moved on to coal. That's when we had the Industrial Revolution, and now it's predominantly crude oil. And so when we take out crude oil, how is it that we are going to refine it? Well, first off, we have to pump it out, and that's called production, and then we go through the refining process, which, remember, is separation by boiling point. OPEC is an important term to know. That's the Organization of Petroleum Exporting Countries. They're mostly in the Middle East, but there are some that are outside of that area. Most notably, remember that Venezuela is part of OPEC, and that's important to us because we get a large percentage of our oil directly from Venezuela. Makes sense because they're close to us, but also makes sense because they're not part of the Middle Eastern cultural issues that we have been confronted with in the United States. So there's a little bit less of political upheaval. Not that Venezuela has necessarily the greatest government, but at least they're friendlier with us than the Middle East is. Some more facts. We get 50% of our crude oil from foreign sources. The Alaska pipeline was built to help increase production of domestic crude oil. Just to the left, which would be to the west of the Arctic National Wildlife Refuge, you have the North Slope, and the North Slope is one of our big areas for production. Types of coal, remember that you should know these 4 types. The first one, not really coal, it's called peat, but it is a form of biomass energy. If you were to live in Ireland, there would be people who would go and collect peat instead of firewood to put into their stoves, their what we would consider a wood-burning stove here in the United States. But they use peat. So it's this very compact, dense, mossy substance. Now that peat, if it's been set for a long time under heat and pressure through the geologic cycle, that will become lignite, which is our brown coal. Then more time, more heat, more pressure, we get bituminous coal, and that's soft coal with high sulfur. And the last type that we get, again, after more heat and more pressure, is going to be called anthracite. Now, as we go from lignite to anthracite, lignite has the most foreign substances, including water, including other impurities. It's going to be the dirtiest to burn, and it's going to be the least energy packed, the least energy dense. We go up to bituminous, and then we go up to anthracite, and anthracite is the opposite. Anthracite is very low sulfur, very low water content, so very dense in energy. Anthracite is definitely the best. What we have the most of here in the United States happens to be the middle, the bituminous coal. And that's all right. It's still a good source of energy. It's just not quite as good or as clean as anthracite. Okay, so talking about oil, remember that production is when we're going to pump it out of the ground. And so when we get the oil out, it causes local ecosystem damage. We saw that firsthand with the BP oil spill. That was from a rig. Usually we're just talking about slow leaks, but the entire, well, you guys remember, the entire rig piping came disconnected, and we just had a gushing of oil from the inside of the Earth's crust. In the transportation of oil, we have seen oil spills that cause local and regional ecosystem damage. So again, first part is production. That would be like the BP spill. Now we're talking about transport, and that would be like the Exxon Valdez spill. So oil spills, again, that one was in Prince William Sound, Alaska, caused a lot of damage to the shoreline around there. And then the final environmental consequence in the final stage of the life cycle of oil is during the use. So as we drive around in our cars, we produce photochemical smog. We get particulates, especially when we burn it. We get acid precipitation, especially because of the nitrous oxides that are released from fossil fuels. And again, that CO2, which is a major contributor to the global climate change issue. Okay, but coal. So what do we got going on with coal? Coal is the dirtiest, like I said before. When we talk about production of coal, we're talking about the mining of coal, however you do that. So it causes ecosystem damage. The least amount of ecosystem damage is done if you do coal mining inside of the mountain, or what we would call subsurface coal mining. And I think you guys know that obviously the most impact to the ecosystem is going to come from that mountaintop removal. Strip mining is also very devastating, but mountaintop removal is even more so, especially because they have to do valley fill with all of the overburden that's left over, and so they're cutting off streams and they're contaminating the groundwater much more so. Reclamation is very difficult because you've taken out a lot of things that produce toxic tailings, and so you get some acid runoff. Basically, you're going to destroy the nutrients that are in the topsoil, plus you're turning the topsoil over and it's not on top anymore. And so that makes it very hard to get things to grow back again and to restore the environment, and that's what reclamation is. Again, I said that there's runoff of acids. You also have those mine tailings. Remember, tailings are toxic. They could be acids, they could be other things like mercury and arsenic, but they're definitely going to be toxic. You get erosion because we've lost all of what was on the surface, like the grasses and the trees. Black lung is a disease that is very common among miners who are working inside the underground mines. And radon, if you're working closely inside the earth, there's a possibility for the uranium, remember, is where the radon comes from, the uranium in the rocks to produce, through its decay, that radon. And if you're working in the mines, you're going to be exposed to that. Now, the transportation of coal is very energy intensive because the best way to transport that is with train cars. And so it's still a fairly outdated mode of transportation, and it's just a very heavy thing to move. Using coal, it's definitely, like I said, very, very dirty. Largest source of carbon dioxide, its greatest quantity of contaminants, especially things like sulfur and mercury. And you get a large volume of waste, and then there's acid precipitation as a result of that sulfur. So again, coal is really not a great alternative environmentally, but we do have a lot of it. So economically speaking, it is very important to the United States, but environmentally it is incredibly problematic. Now, natural gas. Natural gas is what most environmentalists would say is our friendliest fossil fuel because natural gas burns fairly clean and natural gas is not as big of an issue as far as spills and leaks while in the production phase. So it says here it's possibly a transition fuel between fossil fuel and alternative energy sources. A lot of people now, though, are seeing just how easy it may be to switch over to something like electricity, and so that we might not need that transition fuel source. That was back when we thought that we might go to things like biodiesel and synthetic fuels. Now, natural gas does have its issues lately. We'll talk about that in a second. So, environmental consequences for natural gas. In the production of natural gas, this is when we're going to drill it. Local ecosystem damage is possible if oil or coal is part of the deposit. Because remember that typically natural gas is found on top of deposits of oil. Now, this used to definitely be the case that we said, oh, you know what, natural gas is pretty easy and clean to get out. But now we're worried with production about the hydrologic fracturing, because that is causing massive local ecosystem damage to especially the water supply. As they go down and fracture those rocks, remember they're sending a slurry down into that piping to make sure they get enough holes created. And part of that slurry has carcinogens like strontium, and there's other things like the methane that gets released not necessarily up through the piping, but can get released through the water supply of people who have well water. So production, a little bit more sketchy now that we've got fracking going on. Transportation of natural gas can be explosive, and so that is a problem. It's very hard to ship it because as you liquefy it, remember LGN, liquefied natural gas, then we even become more explosive. Uses for natural gas. It produces the least air pollutants when you burn it, and so nothing else can be said about that. Our biggest problem really is in the production. If we weren't doing fracking, natural gas is simply a non-renewable resource, but is a very clean and good resource for energy. But none of us really just plugs in our iPod or our computer or now our iPhones into a natural gas outlet. What we do is plug in for electricity. That's what makes most of our consumer items go. So electricity, the issue is, where did it come from? How do we generate that electricity? So it's a secondary energy source, meaning again that we have to burn one of our fossil fuels or we have to go through another process to convert a stored energy source to the electric energy. It relies, like it says, it relies on another energy source. Basic production, we've said it over and over again, you're going to heat up something so that you can boil water, make steam, turn a turbine, and then that will turn the generator. The generator is what makes the electrons flow through the wire. So anytime we can get heat, we can produce electricity in this manner. So some examples, we have nuclear power, where we have the splitting of uranium atoms to produce that heat that boils the water. We have coal as our next major production, and then there's oil. Geothermal is another source of electricity where we can use the hotness of the Earth's rocks to boil the water. Solar can also be used. Now remember that there's 4 different types of solar. There's solar thermal would be the one that we could use to create electricity in this manner. We can use photovoltaic cells, but that's not using that boiling water system. Wind is also skipping the boiling to just simply turning the turbines to generate electricity, and same thing with hydroelectric. So it says there, no boiling water required, except remember with solar, you could do the boiling water if you did solar thermal. Okay, so moving on then to other sources that we could use for power for electricity in particular. Nuclear power had been heralded as one of the greatest things coming, especially back in the 60s and 70s. Remember that the U.S. Navy has been using nuclear-powered submarines for a long time without incident. But when we started doing nuclear power plants, it got more into the public eye. Now, the good thing about nuclear power is we don't have any CO2 emissions, and that's not quite true. It's 1/16th, though, of what we would get with our fossil fuels, and no particulate emissions. So it is a very clean source in those regards. The problem is with the waste. So cons, the radiation can lead to damaged DNA. It is expensive. Again, we have that radioactive waste that's left over once we have used up all of the uranium-235 in the fuel rod. And we lead to thermal pollution. But we've seen with the manatees that you can turn that for you. But again, that's not every ecosystem. If you are in the north of the United States, there are not going to be a lot of animals adapted to that type of thermal pollution. Florida is different. They're used to warm, and the manatees love the warm. So basically what you do with nuclear power is split uranium and you give off heat that way. When you split the uranium nucleus, it gives off extra neutrons, which then go and split the next uranium, and you get a chain reaction. So you get this increasing amount of heat. You boil water, turn a turbine, turn a generator, and there you've got your electricity. And so one of the other things that we have to remember with the environmental impact of nuclear is that uranium has to be mined before we can use it. Some terms to remember: fusion is when we combine two atoms to make a larger one. We don't do this commercially. They're doing this in test generators in underground. It's a huge, huge loop that they've built underground in France. But that's combining two things like hydrogen and hydrogen. Fission is the splitting of an atom. So nuclear fission is what we are doing right now. A term that you want to know as well is the NRC, or the Nuclear Regulatory Commission. That's the U.S. government agency that is in charge of monitoring our nuclear power plants. You might have seen them on the news right after Fukushima, and they were talking a whole lot about how this could never happen in a United States facility because the NRC, the Nuclear Regulatory Commission, did not approve any of those types of plans. Same thing with Chernobyl. We had those plans. The same types of architects will come to different countries and say, hey, this is the one that we can build. And the United States Regulatory Commission said, no, that's not going to work. It doesn't appear to have all the safeguards we need. So we are in a good place in the United States with nuclear. I don't want you to be afraid of nuclear and think that it's all negative, but even with those safety standards built in, we have had a minor incident, which makes people worried that there could be a major incident. And then the last term on here, radioisotope, is an unstable radioactive isotope. Okay, so uranium. What kind of uranium do we have to use? We have to have uranium-235 in order to do our nuclear fission and breaking apart. Uranium-235 gets hit by a neutron and it's split into two smaller elements, and then those extra neutrons, like I said, keep going on to split up more uranium-235. Most of what we have in nature, though, is uranium-238, and uranium-238 is not able to be used in a nuclear reactor. And so this is why we talk about it. It says in this next bullet, it says it must be purified, but what this is typically referred to as on the news when you hear about it in other countries is enriching. Enriched uranium or enriched plutonium, if we're talking about those Middle Eastern countries or North Korea. Again, we talk about the enriching process. So what this tells us is that we have to take the U-238 and get it at least to 4% U-235 in order for this nuclear chain reaction to start occurring, and that is an expensive process. So how does a nuclear power plant operate? This is a water-based system here, and you can see that there are multiple loops of water. The first that you see right here is the backup cooling water, but there is water contained in this vessel right here. Now this water will simply circulate in this loop. We have another loop of water right here, and we have another loop of water from the exterior into the cooling and the condenser inside of the generator tower. When you see a picture, when you see a picture of a nuclear power plant and you see the big tower with all of the smoke coming out of it, that's really steam coming out, and that is from this segment right here. This, even though it looks gigantic, really is not. This is not a large piece. What we see the most, like I said, is this piece right here. Okay, so we use water a lot in our system of nuclear power plants. Water is used as the moderator right here. It's going to slow down the neutrons so that we can control the speed of the reaction. The other thing that's inside, besides the fuel rods, which are shown as the black, we also have control rods, possibly made of boron, that's one of the most common, that we can put in and out of the reactor to speed up or slow down based on what we need for production. So in the middle of the summer, when everybody's running their air conditioners, we might need to pull most of those control rods out. But if something happens and we have an issue, maybe we're losing feed water like they did in the movie clip that we saw, then you might put those control rods back down to slow down that nuclear reaction. So you've got your fuel rods, you've got your control rods, and you've got your water. Now, as this water heats up, because of those nuclear reactions, the water is going to cycle, and it's going to be pushed through this pipe here. And again, it's very hot, so as it comes into the next water system, it's going to boil that water, which creates the steam. Here's my pointer, which creates steam that goes up, turns the turbine. Well, as it's coming through here, it's cooling down because it's moved away from that hot water. And so then it goes through the condenser and it gets pumped back around again. So this is a secondary loop. And then, in order to make sure that this cools down back to a water form and isn't just hot, but not as hot water vapor, we have another water pool here that goes from the exterior of the plant back in. And so what they'll do is they'll locate near a river or near a lake, and they'll be pumping that water in. That helps to cool down the steam gas and create water again. And so we get our heat there. Now, if you think about it, then this is a lot of safety. This water is definitely radioactive, but this water, depending on how you're piped, isn't very nuclear reactive or isn't nuclear reactive at all. And then we go out here and we're now outside of the containment shell, and there should not be radiation leaving through the water supply. So let's see, I talked about the neutrons, talked about the fuel rods. Approximately a third of them have to be replaced each year. So again, it's not a total turnover. Fuel rods are pretty big. They've got a lot of uranium in them. Heat transfer system, I talked a little bit about how the water slows down that heat process so that by the end we don't have as much thermal pollution. So you need to have that cooling system there. And there are redundant safety systems. You've got your reactor vessel. We even saw in the picture in our book that inside that you can have a pressure vessel. And then outside of that is your containment building, so that there are multiple safety systems built in. Now, disposal, this had been the idea, is to bury it in a place called Yucca Mountain that's in Nevada. It says southeast Nevada. Well, the southern part of Nevada is pretty skinny, so southeast Nevada, I'm not sure how far up they're going, but the southernmost part of Nevada is pretty close to Las Vegas. So, again, that became more of a concern as Vegas hit sort of a rebirth and has now become a more popular tourist destination. But one of our major concerns is that, and this one isn't even on this list because of when this PowerPoint was made, our major concern right now is that in transporting all of that fuel to this location, we put ourselves in a huge risk for terrorist attacks, and the kind that would release enormous amounts of very detrimental radioactive gases into the atmosphere. But the other thing that we realized is that this is still a geologically active area. There's possible intrusion from the water table, which could create problems as the radioactivity seeps down into the aquifers. Again, talk about the distances for waste travel in terms of just the fossil fuel use required, but also that sets us up as a terrorist target. And remember that we have to monitor this for thousands and thousands of years because the radioactive decay, the half-life of this byproduct waste, is incredibly long. We have had accidents. Most notably was Chernobyl, although most fresh in your mind is going to be Fukushima. But Fukushima still did not have the amount of radiation released that they did in Chernobyl. Otherwise, we really wouldn't be seeing people living in Japan still. because what happened in Fukushima was explosions that were outside of the containment. And so we didn't get exposure of a lot of that nuclear product like we did in Chernobyl, where the containment blew up. But Chernobyl was in 1986. It was in the Ukraine, former USSR, and it was a complete meltdown, meaning that it completely blew. There is no more containment left. They are talking about going in, the United Nations, along with its member countries that are the developed countries. We are talking about going in and recapping the site because there's too much radiation leak still. 3 Mile Island is our big incident in the United States, and so it can also be considered the first major incident. Even though we don't do most of the nuclear power in the world, France is a leader in terms of percentage of the energy that it uses from nuclear. I believe South Korea is the other one that's wired up there with France. But 3 Mile Island happened in 1979 in Pennsylvania, and it was a partial meltdown. Nobody was known to be hurt. There was very minimal radiation leakage. And remember, radiation is all around you anyway because of the atmosphere that we live in, because of the sun, because it just happens to be everywhere. And so while there was a little radiation leak, it's not considered to be any amount that was threatening or dangerous. But coupled with the timing of the China syndrome, this then became incredibly tumultuous in the public eye. Now, chapter 15 talked about renewable energy, things like sunlight, wind. Oh, again, and in our book, this is not chapter 15. I believe this is chapter 16. But we talked about sunlight, wind, water, and that could be falling water like made in a hydroelectric dam, or you could even use smaller scale moving water like in a tidal system. Geothermal energy. These are not fossil fuels and not nuclear. Those are the ones that are non-renewable. So always remember that non-renewable does include the nuclear power as well. So anything else, they call it, now typically we call it alternative energy instead of just renewable because it's potentially renewable. We can, with geothermal, put too much water down and cool the rocks and have to wait an extremely long time to get the heat back. So again, it's not always purely renewable. We still have to be smart and be careful. Okay, indirect solar power. How does the sun affect wind? Well, we get wind because the sun heats different areas of the earth differently depending on the tilt of the sun compared to the earth and the seasons, and so we get wind as a distribution of that heating. Hydropower, well, the sun is responsible for making water evaporate, which then makes water fall down and flow, and so the sun is indirectly responsible for that. How is the sun responsible for firewood? Well, without the sun, you don't get photosynthesis, you don't grow any wood, you don't get any biomass that way. Even the hydrocarbon fuels, even our fossil fuels, come from indirect solar power. The sun made those organisms grow millions of years ago, and then they got trapped, buried, and now we've got fossil fuels. The only sources of energy that do not have to do with the sun are nuclear and geothermal. Those are completely created by the Earth's geological processes, not solar energy. Everything else comes directly or indirectly from solar. So obviously, if the sun is the source of our energy, then the most efficient thing to do would be to go straight to the source. So we've got 4 types of solar energy. The first type is passive solar, where you're simply talking about heating. This is a window. So you'll see your cat sitting next to the window. He's getting warm. He is using that passive solar energy. Active solar energy is, again, only going to be used for heating. This is doing something like putting a collector on your house. What you'll have is a fluid that runs through the tubing on top of your house. It's lined with black to absorb the solar energy, and then that can come back through your house. You can use water directly, and then that can just be your hot water heater. Or you could put another type of fluid through there, and you could run it through your house as a radiator device, something that creates heat in the winter. Thermal solar is used for heating, as in a solar cooker, or it can be used for electricity. This is where we're going to concentrate all of the mirrors onto one surface, and then we're going to use that to boil water to create steam, to turn a turbine, to turn a generator. And then photovoltaic is are example where we simply use silicon cells that have been created to convert the energy from the sun into electricity. And so silicon, again, is the thing to remember. In the early days of solar energy, you had a lot of people complaining, well, this isn't really a clean source of energy because when you make the solar cells, you're using things like silicon. People now pretty much back off of that, especially as solar cells are becoming more and more long-lasting, and so they're not as disposable. Okay, I want to go back for a second because we also talked about wind energy. That's become much, much bigger lately. So remember that with wind energy, we build a wind turbine and it just simply captures the kinetic energy of the wind, turns it into electricity through the turbine and the generator. And there are a number of others. Again, you've got your tidal, you've got hydrogen fuel cells. So there's a lot more to explore here, going back into your notebooks or going to one of those other PowerPoints or to the student review pictures. Okay, then we talked about risks and pollution. One of the things listed up here is the Borneo. Remember we did the cats of Borneo activity where we looked at why they had to parachute cats into Borneo. And it was because they had sprayed DDT to kill off malaria, but that had in turn killed the lizards and it infected the roaches, and then the rats took over, and then there were no cats, and so they had to parachute cats into Borneo. Okay, so starting out though talking about risks and hazards. A hazard is anything that causes injury, disease, or death to humans. It causes damage to property, or it causes destruction to the environment. We do have cultural hazards, and those are things that people choose to engage in. Now, your choice might be a little bit pressed. If, for example, you grew up in West Virginia, you might be forced to be a coal miner because that's about the only options you see in front of you. But there are a lot of other cultural risks that we choose to engage in, like skydiving or smoking cigarettes. Risk is the probability of suffering as a result of a hazard, and perception is what people think the risks are. So we have things like there are more people frightened of flying in an airplane than frightened of being in a car, even though the risk of injury in an airplane is far, far less than the risk of injury in an automobile accident. So cigarette smoking is, of course, one of those types of cultural hazards. It's the leading cause of cancer in the U.S., can cause cancer, lung disease, and a bigger risk of death if you have other exposures to other types of air pollution, most notably things like asbestos or radon. Those are going to increase your chances that smoking can kill. So it becomes a high health risk in the United States. Obesity is now, though, a bigger health risk. Insecticides and pesticides, so talking about some toxins that we are using and that we are exposing ourselves to. One alternative to using those is to do integrated pest management. And what that is a system where you might still use chemical pesticides, but you're going to include and coordinate other things that deter pests. One might be adjusting environmental conditions, another disease-resistant crop varieties, rotating your crops so that if you've got a pest that has come in and knows that you make corn every year, we'll switch it out with soybeans and they'll have to find a new home. And hopefully when you come back to corn, they don't come back right away or they don't come back at all. And then you can use biological controls. Things like ladybugs are going to kill aphids. So if you have a rose garden, put out a bunch of ladybugs. If you have other types of gardens like vegetable gardens, you might try putting out praying mantises. You can buy praying mantis egg sacs and then you can let them hatch, and those praying mantises will prey on the insects that are eating your garden. So you've got a couple different carnivorous insects that will help take care of your herbivorous insects. What we need to know too, insecticides kill plants, mammals, fish, and birds. Really, I wish it had said pesticides there. Insecticides kill insects. Pesticides can kill plants, like an herbicide. We've got rodenticides. Those would kill mammals. We've got things that will kill fish. And I think what they might be trying to say here is that if you spray for these things, you could have these effects as well. And we also saw that DDT, which was meant to kill the mosquitoes, but it also had an effect on the bird population. A broad spectrum pesticide is effective on many types of pests. So you might buy it thinking, oh, I'm going to spray Roundup so that I kill off all my weeds, but you might end up killing off more than just the weeds. A little bit about DDT. Remember, this was Rachel Carson's big deal. We've got a couple ads here for DDT, and both of them are a little bit funny when you start to look at them. First one you've got there, an elephant spraying DDT with his nose, and the other one is a house mom spraying DDT inside of her house. What we didn't know at the time is that DDT accumulates, that bioaccumulation. It gets into your fat tissues, and it's not water soluble, so it doesn't come out. DDT was not used for handling weeds. DDT was used for insects. And DDT, we found out, was a persistent synthetic organic compound and subject to biomagnification in food chains. So again, it accumulates in your tissues, it magnifies as it goes up the food chain, and then that was why the predatory birds, the things like the hawks and the eagles, were the most affected by it. Some diseases to know about: Lyme disease. Lyme disease comes through a tick bite. Mosquitoes carry malaria. Again, malaria is not brought to you because of the mosquito. It's brought to you because the mosquito carries the plasmodium that creates malaria. The mosquito is just simply the vector. It's going to transmit the plasmodium of malaria. But mosquitoes don't necessarily carry malaria, especially the ones that are here in the United States. Now, as climate change continues, the Anopheles mosquito, the one that can carry the plasmodium, its range is starting to spread out. So again, just remember that the causative agent of malaria is the protozoan. Okay, so here's a tick picture. It's actually an Asian tiger mosquito. You can see the banding, especially back here on the tail, which lets us know that it is an exotic species. Invasive to the U.S., came in a shipment of tires. More stuff about diseases. We lack access to safe drinking water, and that's a big reason why people face disease in developing countries. Epidemiology is the study of the presence, distribution, and control of a disease in a population. Morbidity, the incidence of disease in a population. Mortality, the incidence of death in a population. Water pollution. All right, we've got some issues with water pollution, but luckily, back when we did the Clean Water Act, we started to require sewage treatment. So sewage treatment is a common practice, and that has helped considerably. In the 1970s, it says many cities were still dumping raw sewage into their waterways. Well, no wonder Lake Erie looked disgusting. If you've got all those different cities just dumping everybody's feces and pee and everything into the rivers and lakes, of course it's going to be pretty contaminated. So in 1972, the Clean Water Act provided funds to upgrade sewage treatment plants, and now you have to do step 1 and 2. Remember, you can opt out of 2 if you get a hardship finding for your economic standing, but we definitely do have step 1 and 2 required, and then it's not really a step, and then chlorination or disinfection is also required at the end of the process. Currently, waterways are much better than they were in the 70s. Well, you can just think about that. If you had raw feces going into the water, that makes us just about the same as a developing nation. The first and second, they call it degree. We just called it first step, second step. Use preliminary methods of reducing water pollution, but no more. Remember, first is primary treatment. In primary treatment, we're doing physical. The secondary treatment is where we use the biological. We're going to add the bacteria, and we're going to add some oxygen for them. When you go through your sewage treatment, at the end you need to test for sewage contamination, like fecal coliform. Now, for drinking water, you are not allowed to have any colonies of fecal coliform. So sewage treatment, 99% of raw sewage is just water. So we're talking about treating that 1%. So in your preliminary treatment, or in what we call primary, you allow the grit to settle. Remember, we had the grit chamber, and then we had like a blender where we would mush it up and then move it on to the next stage. And so the first thing we want to do is separate the sludge from the water. The second thing that we want to do is get the bacteria to eat up the organic stuff. And so that's, again, where we put the bacteria in, and we have to add oxygen so that they can, as they eat, they can not run out of oxygen, which would force them to die. You also have, it says trickling filters that contain bacteria to remove raw sludge from the water. We talked more about a slurry mix. That tends to be how they do it nowadays. Raw sludge may contain heavy metals, and so if you ever go to get compost material or fertilizer material from one of these treatment plants, they'll tell you not to put it on any edible foods. You can't put it on your garden, you can't put it on a farmland because it could contain heavy metals, and you don't want that getting into the food that you're going to eat. If you need a third stage of treatment, If you need a third stage of treatment, then you are going to be talking about chemical treatment. And in that chemical treatment, you're going to target specific items, like perhaps nitrogen, or maybe you want to target something like fluoride. I don't know what you're going to target. Nitrogen tends to come up a lot because of the fertilizers. Now, if you do that, it is going to be incredibly expensive, and you can only treat one chemical at a time. So that is not required, but some communities elect to do it because it is going to make it easier for them in their drinking water system to make sure that your water is clean and clear of pollutants. Remember that the last thing you have to do is, again, go through that disinfection. You can do that with chlorine. You can do that with ozone as well, UV rays. You can just have the water sitting out for 3 days and that'll be enough time for a large amount of water to get cleaned. Remember, if you put a plastic bottle out for 3 hours, it can get cleaned from the sunshine, the UV rays. Okay, your home septic system, if you're not on a sewage line, does the same thing. Typically does not use chlorine though, because that chlorine would kill all of those beneficial microbes and it would get directly into your yard and it could kill your grasses. It doesn't have anything but the one tank, and so it does allow things to settle a little bit, and it allows some bacteria to go in and start breaking down the waste. But the big thing is that water, remember this is 99% water, the water is going to come out and percolate into your yard, into your field lines, and it's just going to seep out and help your grasses to grow. And so that's the basics between the most simple form of a septic system. Septic systems have come a long way, and if you had to get a new one because your old septic tank had broken, then you would get a 3-sectioned septic tank that pretty much functions like the 3 sections of a sewage treatment plant. And so that's pretty neat as well. But again, this is the old-fashioned system, the most basic. Okay, we did not get to municipal solid waste in class at all. Municipal solid waste, when you hear the term solid waste, it is talking about trash. Trash, not poo. So MSW, municipal solid waste, most of what we make here in the United States for waste is paper. Again, paper could have been recycled, but it's still a major contributor to our landfills. 55% of our MSW is disposed of in the landfill. So the next obvious question is, well, if it's not going to the landfill, where is it going? 17% is combusted. So a lot of people say, why don't we just burn our garbage? And some of it does get burned. Most of the time, if you're going to burn it, you're going to use what's called waste to energy, WTE, combustion. The reason for this is, remember, anytime we can get heat, we can boil water to create steam, to turn a turbine, to create electricity. So if you're going to be burning trash, why not go ahead and turn that into electricity? And so that is a good part of waste to energy, but the bad part is that waste to energy creates a lot of toxic fumes because not everything that is disposed of in the trash should have been. We can't burn plastics, they'll release toxins and dioxins. The best solution is reduce the waste at its source. Okay, so remember your 3 R's: reduce, reuse, recycle. Reduce is number 1. If you can reduce the amount of trash that you make, and that might be by consuming less, or it might be to choose different types of packaging, but that's going to be the biggest way that you can alleviate your solid waste problems. More than 75% of municipal solid waste is recyclable. Maybe not at our school, but especially at home, you have the option to recycle all of your cardboard, all of your paperboard, everything that's paper. You can recycle receipts, you can recycle magazines, you can recycle glass, you can recycle metals. There are a lot of things that can be recycled. And so recycling is a great option, but when people see that the cost to them, and the cost here might not be any money, it might just be in terms economically when we talk about cost and benefit, it might just be the burden of going out and getting a recycling bin, or if you're at school, the burden of locating the closest recycling bin. So we can do a better job at recycling, and the way that other countries have done it is to start charging for the amount of garbage produced. And so if you start charging for how many bags of trash you have, you got to figure out a different way to do it. Japan has an incredibly complex system of sorting garbage and making sure that you're recycling everything that you possibly can. Germany also does a very good job with its recycling program, but again, it all starts because you have a pay as you throw system. You pay for the garbage you throw away. And so think about what that would look like. Now, hazardous waste, again, we didn't get around to this part of the unit. We did talk a little bit about it when we talked about different types of pollution, especially when we looked at the Woburn, Massachusetts case study. So hazardous waste is those things that are compounds, they're toxic to us. They talk about here that some of them are pesticides, some of them are used to make plastics, but they're resistant to biodegradation. And so, again, in our movie, they talked about TCE, tetrachloroethylene, so organic compounds where we've replaced, it says using these are halogenated hydrocarbons, but hazardous waste can be any of those types of compounds. Chlorinated hydrocarbons, here we go, so this is like TCE. They're synthetic organic compounds, so they're organic because they contain the carbons and the oxygens and the hydrogens, but we've added some things to them and made them not quite biodegradable. So dioxins are an example. Mainly this is caused by burning PVC pipe like medical waste. It's linked to cancer. Also an endocrine disruptor. And so let's talk a little bit more about endocrine disruptors. Remember that these are things that interfere with our normal hormone action. Your endocrine system is in charge of your hormones, releasing estrogen, testosterone, your adrenaline, all of those things that are going on in your hormones. So if you get the wrong amounts of those released, it can interfere with your development. It could stunt your growth. It could even do so much as stunting your sexual development or increasing your sexual development. Both are problematic. Often this is connected to cancer eventually. It can interfere with sexual activity. I always tell my classes about the alligators in Florida and how the male's size of their reproductive organ is no longer sufficient to impregnate the female simply. And so the excess estrogens that have been added to the water have femalized them to the point where they're still male gators, but they simply aren't functioning the way the male gators need to function. And so again, we get a lot of these in plastics and some in pesticides. So when we start talking about the pollution issues and people throwing away plastic bottles in the Pacific Ocean garbage gyre, then we start to see some of these really problematic issues. BPA, which has just recently come out to be one of these endocrine disruptors, again, just got removed from our plastic water bottles about 2 years ago. And we've all been drinking out of these plastic water bottles for years. It's still coincidentally in a lot of the plastic bags that our food come in. And so you're being exposed to it even if you think you're not, even if you're like, oh, well, I buy a lot of produce. Yeah, but do you put it in a plastic bag in the grocery store? Because if you do, and most of us do, we grab the little plastic bags for our produce, then you're exposing it to BPA as well. You need to make sure that you wash that produce very thoroughly if it's been in one of those bags. So the Love Canal story in New York, a lot like our Woburn story as far as what was going on, was the bearing of toxic chemicals. But Love Canal is a little bit unique because it was first, the government allowed a housing site to be built over a toxic waste dump, and then people got very ill. They first discovered the problem in 1978, and it was a national emergency in the U.S. because of this toxic waste. It was located at a school, and you had children getting enormous rates of cancer. And this is what led to the Superfund legislation. So as opposed to in the Woburn, Massachusetts case study, in that we saw a civil litigation suit. But with Love Canal, it was a government-enacted program. So it led to Superfund legislation. Where does Superfund money come from? From the taxes on the chemical industries. And those taxes are meant to help clean up those Superfund sites. 50% of them end up getting spent just on the legal cost, though, of trying to bring the parties that are at fault to justice. Okay, layers of the atmosphere starting from the inside. We have the troposphere, that's down here. We've got weather down here, that's where we are. Then we've got the stratosphere. In the stratosphere, you have the ozone layer. The mesosphere is where the meteors burn up. And the thermosphere or ionosphere is where we have solar radiation being deflected from the Earth. And so we end up with the aurora borealis as that occurs. So in the troposphere, remember that 78% is nitrogen, 20% is oxygen. I don't think they'd ask you the specific numbers, but that makes up the majority of our atmosphere. So the other 2% or less is water vapor, argon gas, carbon dioxide, and then other trace gases. And so again, you can see depending on where you are in the world, you're going to have more or less humidity. But you can see based on those numbers that when we start talking about the global greenhouse gases, we're talking about a very small composition of the atmosphere. And so very small increases in carbon dioxide lead to very big problems with temperature. And so again, it's just important to remember that because people will say, well, yes, but humans have been here forever, or it's the cows, or it's this or that. Just think about how much our population has grown and that inevitably is going to cause some fluctuation in these numbers and eventually be problematic for the balance. Okay, global warming, so talking about that CO2. Normally we have those greenhouse gases, which are things like CO2 and methane and nitrous oxides, and they're going to help to keep us warm enough for life to exist. So the greenhouse effect is good. It's up there in green. Global warming or global climate change occurs when humans are doing too much to make many more greenhouse gases than would naturally be present. And so that leads to an increase in temperature. It says small, 1 to 3 degrees. But again, that is significant in terms of global averages. The analogy is a car on a sunny day. Your car is sitting in the same environment you are, but it gets warmer and warmer because it's trapping that heat. Now a little bit about the ozone layer. The ozone layer, the ozone layer is in the green one. Let's start with the one in the troposphere. The ozone down here is bad. If we breathe it, we get lung disease, we get respiratory failure. It's also a greenhouse gas. When it's down here, and it gets down here because of cars and other high temperature motors running. The ozone down here is bad, and it cannot get up to the stratosphere. But the ozone that is in the stratosphere is very good. It is the Earth's sunscreen. It shields us from the harmful rays of the sun. Remember, there's UVA, B, and C. Almost all of the C gets blocked by the ozone layer, none of the A, and most of the B. And so it's really that UVB that we're concerned with, because as the ozone layer has thinned out, more and more UVB light is coming through, and the UVB is more powerful than the UVA. Ozone depletion is, again, the thinning of the atmospheric ozone shield. The biggest thinning is occurring over the South Pole. And so in Australia, you have immense thinning where even possibly some UVC light starts to get in, which is even higher. Now in Australia, if you were a small child, you have to wear a hat out to recess. They have covered playgrounds. It is very big to think about constantly your sun exposure and how you're going to deal with that. So again, the analogy stratospheric ozone is like the sunscreen for the Earth. Okay, now moving on to air pollution. Air pollution is a very expensive problem. It increased our healthcare cost. It has a massive impact on human lives and human death. You can talk about pollution having acute effects and chronic effects. Acute are effects that happen very quickly. They can be bad, or it could just be something like nausea. It could be something like death. Chronic is something that is long term. Again, it doesn't mean that one thing is better or worse. Chronic could be something like cancer. And so you see the next term there is that these air pollutants are carcinogenic. Air pollution also damages buildings, bridges, statues, books, especially when we start talking about acid deposition. Acid rain is actually going to have an impact on the stability of our structures, on the engineering and the soundness of those things. It also impacts our aesthetics. You think about LA and you don't think about bright, clear, sunny skies. You think about smog and yellow, dingy skies. It also causes damage to plants. You can see from this picture here, you've got a leaf that has been decimated, and this is really by air pollution, not by an insect. And so it does cause a loss of about $5 billion a year for agriculture, and it causes death to forests as well, which you could look at from an economic standpoint, you can look at it from an aesthetic standpoint, you can look at it from an ecosystem protection and biodiversity standpoint as well. Acids and bases, just a quick little reminder that the pH of something is the log function of hydrogen ions in a solution. If it's basic, you should have something that is over 7 on the pH scale. If it's acidic, it's under 7. I always like to list it the other way to go acid-base because then it's in alphabetical and numerical order. So remember, acids 0 to 7, bases 7 up. Neutral is pure water. It's going to be a number 7. Normal rain is going to be slightly acidic. This says 6.4. We had it being closer to around 5.6 in the thing that we read from the EPA. But acid rain is defined as anything with a pH of less than 5.5. Indoor air pollution is perhaps more of a problem even than outdoor air pollution because when you're inside you get trapped with those pollutants. So some of the major types to worry about: benzene, formaldehyde, radon, and cigarette smoke. Sources of some of those things are off-gassing from furniture. Formaldehyde is used to preserve things like your carpet, your upholstery, I'm trying to think of the word, your curtains, your rugs, your building materials, all of those have formaldehyde in them. And so the higher degree of formaldehyde, usually the cheaper the product, the more exposure you're going to have. When you bring home your dry cleaning, those chemicals are in there. Cleaning fluids that you might use to clean your house, disinfectants, pesticides, and even your heater, those are all increasing the amount of indoor air pollution you're exposed to. If a building has too many indoor air pollutants, it is called a sick building because people inside get sick because they occupy the building. It could be mold and the mold spores that it gives off. It could be, again, the heating system is faulty. It could be any of these items, but you do have a serious issue that the EPA has recognized and noted is called sick building syndrome. Major outdoor air pollutants, remember that we've got our primary pollutants and our secondary. Primary means we put it up there directly, something like CO2. As we burn fossil fuels, CO2 goes up in the atmosphere. Then you have secondary. It occurs when primary pollutants undergo a reaction in the atmosphere. We release sulfur when we burn fossil fuels, and that sulfur reacts with water vapor to create sulfuric acid, and so that would be a secondary pollutant. Then you've got your list of 6 big air pollutants that we need to worry about. You've got suspended particulate matter, volatile organic compounds, carbon monoxide, nitrogen oxides, sulfur oxides, and ozone. Now, one of the things to remember is that the other list you need to know for outdoor air pollutants is the ones monitored by the EPA, and that's SPLONK. The only difference is that you're going to substitute those volatile organic compounds with lead. Lead is not something we're terribly concerned with anymore because it's not released, but we are concerned more with volatile organic compounds. The EPA still monitors lead, however. Okay, some sources of air pollution. Remember that we can have natural sources like volcanoes, sea spray, or it can be man-made or anthropogenic. And so you see sources there as well, especially when we talk about burning fossil fuels. You'll see that all over the place, coal-burning power plants. And so sources of sulfur oxides, nitrogen oxides, those are all going to be fossil fuels. We have effects on areas that are hundreds of miles away from us, even especially places like Canada. Okay, so moving on. Solutions, what we can do, we can reduce our emissions. Something that we could do on the input side is cleaner burning gasoline, increasing our fuel efficiency or our CAFE standards. We can use different modes of transportation, mass transit, using bicycles, using electric cars. We can decrease the number of miles that we drive, change our land use decisions so that we've got more buffers, and we can make sure that our catalytic converters are working, something we have to do here in Atlanta because of the emissions standards. Or we can control it on the output side. This isn't nearly as effective because the pollution has already been produced. We simply need to make sure that we contain it. And so a scrubber is something that is put into a coal-fired power plant, and that scrubber can then reduce the sulfur content. It's sort of like a sponge on the outside of the pipe. And so it's going to help reduce the amount of pollution that reaches the atmosphere. We can also wash our coal before we burn it, and that's what clean coal is. Problem is, again, all we've done is moved the sulfur to the water system. Or we can use fluidized bed combustion. It's sort of like that idea with a scrubber. We're gonna get that waste ash that we have to dispose of somewhere else, but we've burned the coal in a fluid bed so that we're containing it instead of losing it to the atmosphere. And that's the end of part 3.